So, welcome everybody. So I'm today for the stuff. Good month. No, for the stuff means good month.
Oh.
We got a little bit mixed up with fractals and networks, but that's life. Okay, everything changes. It's dynamic. And today we will have a tutorial on fractals, in particular Koch and Sierpinski triangle and Koch curve, and Ethan will tell us, remind us what is fractal dimension, how to calculate it, and after his tutorial I will continue with the networks, and we will talk today about Basilians and prepare ourselves for next week when somebody is, I forgot who's going to talk next week about resilience of networks, and when you kick out nodes, how do you affect the functionality of the network, but this we will have afterwards. So Ethan.
But resilience is connected to fractals.
Resilience, yes, everything is connected to everything.
Yeah.
All right. So my name is.
You need a stick?
No.
No?
My name is Ethan, and today we'll talk about fractals, and more specifically, calculating the fractal dimension. So first off, we need to define what a fractal is, right? So a fractal is any geometric shape that has arbitrarily fine detail, which means that no matter how much you zoom in on it, more and more, you will still see more things, new things, right? So for example, the Mandelbrot set is a very famous example of this. You can see that we're zooming in on it more and more, and yet it never becomes flat, it never becomes uninteresting. It always has more and more details. Something unlike this is a square. You zoom in enough on a square, and it's just a straight line. There is nothing interesting about it.
But you remember that, sorry, I all the time will interrupt you. And feel free, right? It's a tutorial. You should, because what Ethan is putting here will be later in GitHub, and you can use it for your final project. You don't need to use it, everybody who's doing a final project. So, about definition of fractals, what did we learn?
No matter how much you zoom in, the dimension of the space is you don't know.
Self-similar, doesn't matter where you are. You can so magnify.
You don't know where you are.
But in general, about the definition of what is a fractal, Mandelbrot attempted, I think, 3 or 4 definitions, and everybody attacked him. In the end, he gave up. And there are many definitions of fractals. So this is one definition. Another definition is the scale of variance that we talked about. His first definition was about any object that has a Hausdorff dimension of this and this and this is a fractal. All the time people found exceptions, and then in the end he gave up. But it's all right.
So yeah, this is one sort of literary definition. This is not a mathematical definition, but still it is good enough here. And you talked about scale invariance. A lot of fractals exhibit self-similarity, which means you zoom in enough on them, you will see another copy of themselves. So, for example, the Mandelbrot set, or at least a part of it, looks like this. And you zoom in enough, and it looks again like the same thing, right? So that's self-similarity. So now we'll go over some very classic examples of fractals. And the first one, and one of the first to be sort of discovered and analyzed, is the Sierpinski triangle. So the Sierpinski triangle has a very easy definition, very simple definition. You take an equilateral Schwiz-Note triangle, so, and you fill it in. And then you erase from it a triangle upside down, half its size. So I'm denoting erased by red. And then you just repeat this process for each of the 3 smaller triangles that you created, right? So again here, you take this area and you delete it. take this area and you delete it, and you take this area and you delete it, etc., etc., etc. The amount of areas you delete, by the way, grows exponentially with the layer. I'm sure you can see this. So these are the 3 steps. A very simple recursive definition. You take an equilateral triangle, you remove an upside down part from its middle, and you repeat, right? And this goes on to infinity. And now we'll try to follow this definition up to some finite level with code, right? So we import the libraries, whatever, axes, and then we define just a unit triangle, 0, 0, 1, 0, and the correct height on a half, right? This is the correct height for a unit equilateral triangle. And then we define sort of the position of the hole with respect to that triangle. So this is 3 over 4, square root of 3 over 4. You will see later why this makes sense. And now we get to the function that actually calculates where the holes should be. So this is Sierpinski holes. This is the limit of the recursion. If our level is bigger than the limit, we just stop. We don't return any more holes. We return an empty set. But if not, we set an empty array of holes, and then we have to actually create the hole that's in the middle of the triangle, right? So lower left is an input of the function, and that is just the position of the big triangle. So for example, for the first triangle, if these are the axes, its lower left will be 0, 0. This is a bit crooked, but it will be 0, 0, right? So the position of the hole will be lower left plus the position of the hole with respect to the triangle minus the unit triangle over 2. Over 2 so that it's half the size, and minus because the minus flips it. So it's an upside down triangle. And you have to multiply by the scale because the triangles are getting smaller and smaller, right? And then it recurses. For P in unit triangle, it does the same thing for P. Now P are the positions, so if you do P over 2, you will get this, this, and this, right? Or, sorry, actually, this, this, and this. So that's how it can very conveniently recurse on the smaller triangles. Because you take sort of this area and you split it by half, you get this, etc., etc. So that's how it recurses, and in the end, it returns the holes.
So you go on the x-axis and on the y. How do you?
So basically, because I go on the positions in the unit triangle, and I split them by 2, that just brings me sort of the midpoints of all the 3 axes, and that way you do it on the 3 smaller triangles. And that's just how you do it, and obviously you do n+1 so that you're on the next level of the recursion, and you plot this, and in the end, you get this.
Wow.
Alright, so this is the Sierpinski triangle.
How many iterations?
Yeah.
So this is, I was about to say, this is up to 7 iterations, and you can see that already we really cannot see the difference between whether this is finite recursion or to infinity, right? This looks very good. So that's that. That's the Sierpinski triangle. Again, 3 very simple rules brought on this fractal.
Can you do 10 just
Sure.
to see if
I don't think it'll change much,
there's any difference?
but I can do lower because then you'll see sort of the steps.
do lower.
Yeah.
Let's do first 10 and then 3.
So let's see. I hope the Wi-Fi here is okay.
It's a bit on the weak side.
Yeah, 10 is actually a lot now that I think about it.
Yes.
Yeah, 10 takes a bit.
Check how much time you can check.
Oh, here, now it's plotting. You can see it's on this part plots all the polygons, all the triangles.
But you run on Google servers, they should be fast. But we don't have it.
Maybe they're not very invested in this
We
project.
get only the credit ones.
Yeah. So, okay, we'll see. Doing the lower levels is much easier.
Yeah.
So we'll come back to this. Then you have the Koch curve. The Koch curve is also made...
Koch.
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 Yeah, you have the Koch curve.
German mathematician.
Yeah.
Koch also means chef, you know.
Really?
Yeah.
Okay, so it's the chef's curve. And you construct it also with three very simple recursive steps. You take a straight line segment, you split it into 3, you delete this, you ignore this, and then you make a bump which also has the same length, its sides have the same length as these. Okay? And then you just do this recursively for the 4 smaller lines that you have created. So this line segment, you split it into 3s, and you make a bump. This line segment, you split it into 3s, and you make a bump. Same for this, and same for this. And you do this recursively to infinity. Okay? Oh, this is the 10 layers, and you really cannot see the difference.
Now do 3.
Here's
3 should be quick.
Ah.
There it is.
Yeah, very nice.
Yeah, so you can see how this is constructed layer by layer. In the next layer, all of these smaller triangles will also get their own triangular point. Okay?
Nice. Okay.
All right. So again, 3 simple rules, and we will try to imitate them up to some finite point with code, right? So here, I use a rotation matrix, right? Because this part is rotated by 60 degrees. And this part is rotated technically by negative 60 degrees. So this rotation matrix will really help me. This is a rotation matrix of 60 degrees. You can just substitute theta equals 60, and you will get this. Okay? And here, I make an array of rotations. So the first part is rotation matrix to the 0th power. Why? Because this part is flat. You need no rotation for this. And then you have the rotation matrix to the 1st power, because the second part of the line is rotated by 60 degrees. And then the third part, because it is rotated back by negative 60, you need the inverse of the rotation matrix, right, to the negative 1st power. So you get this. And then again, we go to flat, which means rotation matrix to the 0. And now this is the function. This is the limit of the recursion. This is our current point. If we reach the limit of the recursion, we go for the base case, which is just a straight line segment, right? The base case of this curve is just a straight line. You will see why this works. And then for each part of the line segment, the 0, 60, negative 60, 0, for each one of them, we recurse. How do we recurse? We say that we want a Koch curve a third the size, because each one of these lines is 1/3 of the total line length, right? So we say we want the Koch curve a third the size, rotated, this is matrix multiplication, rotated by the corresponding rotation that we are on, right? And then we just add those points to the total points, and we have sort of the end point that keeps track of where we are on the curve, so that's where we need to add them, and then we return the points. And in the end, we plot this, and we get this, okay? So this is the Koch curve. If we put 3 of these together, it's called the Koch snowflake, right? And it really also helps here to see the levels of the recursion. So you can see this is the base case, right? Just a straight line. And then we have just one bump. And then we have bumps on the bump, etc. And you can really see where this is going now. And this is sort of looks like the limit, right? Again, this is to some finite point, but at this point, we really can't see even where it stops, especially because the line segment has a thickness, right? So you really can't see. All right, so
basically, in the beginning, you start the whole object, right? And then, you have 2 rotations inside, and then the next iteration, now you go to the 4 different parts inside, right?
yeah,
So
and each of the different parts,
yes,
because of the application of the rotation matrix on the outside,
yes,
let's say that I'm on this part, and I recursively generated what I need.
uh-huh.
So now, in the end, I rotate it all to 60 so that it's in the correct position.
Okay, and where do you account for going through the different elements?
In the 4 rot in rotations.
So this is the rotations when you are already decided on the element. But
Yeah.
When you are now in the second iteration, you have 4 parts. So you start for the third iteration, you go to the first one, and then you have again 4 parts for your rotation, right?
And when
then
do
you
I
go to
stop?
the next.
Yes.
No, how do you account for this? So you go rotation, and then
I rotate the whole thing, and I recursively call it again a third the size, right? And then eventually, it'll stop by just generating lines. There will be a point where it does the 4 parts, and in each part it just does a line segment. This base case is very important. All right. So now we ask a seemingly innocent question, which is what dimension is a fractal, right? So at first, this may seem to have a very obvious answer. Let's say the Sierpinski triangle, we generated it out of triangles, right? This, for example, in the first layer, this is just a 2-dimensional shape, right? I can fill this in. This has an area. This is 2-dimensional. It exists on a plane. So you say, maybe this just goes on to infinity, and the Sierpinski triangle itself is also 2-dimensional, right? And similarly, you would say that the Koch curve is 1-dimensional, because it is generated out of lines, right? But this assumption, or this guess, will lead to these shapes not satisfying one of the most fundamental properties of what it means to have some dimension, okay? So let's take, for example, a square, which is a very simple, clearly 2-dimensional shape, okay? You want to measure the area of this square. How would you do it? You would do it with some sort of base units, right? מטר רבוע, זאת אומרת, משהו כזה, right? So let's say that, for convenience, my base unit is exactly the same area as this square. How many base units will fit into the square? Just one, right? They're the same area. So I'll say n equals 1, which means 1 unit fits into the square. Now let's say that I take this whole scenario, but I say, oh, sorry, there it is. But now I say, okay, let's make my base unit 3 times smaller. The side lengths are 3 or a third the size, right? If it will do it, there it is. How many base units now fit into the shape? 9, right? 9 base units now fit into the shape. So if we call our scaling factor R equals 1/3, right? We made our lengths 1/3 the size. Then n grows by 9, right? And this is a fundamental property of 2-dimensional shapes. You scale, you put a scaling factor on your units, R, and the amount of units you can fit in grows by 1/r squared, okay? Because 1/1/3 squared is 9. Similarly, you can see, I don't have the time to draw this, but this works in 3 dimensions as well, okay? So let's say that my unit cube is the same volume as my cube, only 1 cube will fit in. If I make it have 1/3 the side length, now 27 cubes will fit in. That's 1/r to the 3rd, right, for 3 dimensions, okay? So this is a very fundamental property of n-dimensional shapes. An n-dimensional shape measured by an n-dimensional ruler, so a ruler, an area, a cube, of scale r will have its n volume scaled by r to the negative n, where n volume just refers to the volume in that space, length, area, volume, etc. So here are some basic proofs of this for various shapes. The only shape pretty much in 1 dimension is a line segment, right? So if we have a line segment A to B, we define its length to be b minus a, right? If we now scale our units by r, that's the same thing as dividing a and b by r, okay? You can imagine that if I have a line segment from 3 to 5, then now it's from 6 to 10, right? This makes sense if I have my base units by a half, right? So the length of this, we substitute a/r and b/r, and we just get 1/r times the original length, okay? So this follows the 1-dimensional version of this group. Similarly, for a triangle, the area of some triangle according to trigonometry is 1/2 AB times sine of gamma, where gamma is the opposite angle, whatever. if I substitute in a over r, b over r, c over r, you can see that this turns into 1 over r squared times the original area, right? So this is the two-dimensional version.
Where is the C?
C is represented with the angle gamma, right?
Okay.
It's like gamma is a function of agates.
Okay.
All right. So this is a fundamental property of any dimensional space beyond the specific shapes discussed, right? You can see for any two-dimensional shape that it has a square factor in all of their areas. All right. So what's the big deal here? It seems, after some thought, that fractals don't obey this law. So if we take, for example, the Koch curve, all right? And let's say we have a ruler of some length delta, very small, okay, not this big, much smaller. And let's say that with this ruler size, n rulers fit into the shape, okay? What if we now make a ruler 3 times smaller, right? You remember, for one-dimensional shapes, we would expect n to grow by 3, a factor of 3. And for two-dimensional shapes, we would expect n to grow by a factor of 9, right? But if we think about it, we make our ruler 3 times smaller. Well, every one of these segments is 3 times the length because we originally divided the line in the recursion into 3 parts, right? So each of these line segments has a third the length, okay? Well, if it has a third the length of the whole shape and the ruler is a third the size it was, that means that only one of these parts will have n rulers fit inside of it, right? But we have 4 copies of this. 1, 2, 3, 4. And so the conclusion is that now n is multiplied by 4. The amount of rulers that can fit in is multiplied by 4. But this does not match not 1 dimension and not 2 dimensions, right? This is somewhere in between. So the conclusion is, or at least we suspect, that these fractals have a non-integer dimension, somewhere, for example, for the Koch curve, between 1 and 2, right? All right, so let's try to define what it means for a shape to have some dimension with this property, and not say that it's just a property of dimensions, right? So a fractal embedded in d-dimensional space, which just means that, for example, the Sierpinski triangle, if you remember, is embedded in 2-dimensional space, right? That's a space it exists in. So a fractal embedded in d-dimensional space is big D-dimensional if scaling our d rulers, so length, area, volume, by a factor of r, grows its volume by r to the negative d. Okay? So it doesn't work for d equals 1 and not for d equals 2, but we want our number d to be the number for which it does work, for which they do scale with that. Okay? And that's how we define their dimension. So let's actually try to do this in practice. Okay? So according to this definition we just saw, the volume of the shape is proportional to r to the negative d. Okay? But the volume and the amount of areas or volumes we count is the same thing, right? So n is proportional to r to the negative d, the amount of rulers we count. You take the log of both sides of the equation, and you get that log n is some constant minus d log r. And if you take differences, this constant disappears, right? And so, then you divide by delta log r, and you get that d is negative delta log n to delta log r, okay? So this is a very good way to find d. We test several ruler sizes, or unit area sizes, or unit volume sizes, and as they get smaller and smaller, we see how n changes with them, you know, because as we make a ruler smaller and smaller, we can obviously count more rulers in the shape, right? So we see how n changes with that, and on a log-log plot, the slope of this line is the dimension. So let's do this for the Koch curve, okay? We define a simple function, count rulers, which gets a list of points and the ruler scale or the ruler length, or it goes over the points. And when it finds a point that is an r's distance away from the point we are on, it counts one ruler. And then it moves on to the point we just counted. So basically we can imagine that if I have the Koch curve, I start from this point, and I go until I reach the length of r, and I count one ruler, and then I go to this point, and I keep counting, and reach another length of r, etc. Okay? So we generate the points for the Koch curve, the same function we used before, and we generate a list of r's, logarithmic, and this is where we count our n's for various r values. And then for r, we just append how many rulers we counted with the function above. And we get this graph, okay? And this graph, we fit a line on it. And the slope of this line will be the fractal dimension of the Koch curve. And that turns out to be about 1.27. So the Koch curve is 1.27 dimensional, okay? And analytically, we can do this as well, according to what we just seen. If we make our ruler 3 times smaller, it is exactly, analytically, 4 times the size. And from this, we can deduce that its dimension is log 4 over log 1/3 with a minus sign, which is about 1.26, which means that we are within 1% error. So this is a very good measure. Similarly to this, we can do the same thing to the Sierpinski triangle.
Good. Before you continue, question to the class. Can you go show the figure? If you look at the figure,
It's a Paolo.
what do you think?
It's Paolo.
I mean, it's Paolo. Yes, yeah, that's the first thing. And what else do you see? It's always good to look at figures.
You see like
the oscillation is the kilo.
It jumps.
Okay.
You see the matricot there, right? You have 3 points, and then it goes down. It's always the same pattern. You see this?
1,
No, but
2,
it's
3.
but
No.
More or less.
No,
Yeah, it's more or less.
more or less.
But you have all the time
You
this
have
matricot
these
of
three,
3 points.
It's like
So
steps.
why is it? Very good answer. Every time it's numerical. As soon as you compute something, it's numerical. No, but I mean, why do you have this? What happens when you imagine it? What he's doing? He's putting a ruler. So, okay, so you can explain. Yes.
Okay, so the reason this jumps is just because this is exactly when a whole new ruler can fit into the shape, right? If not a whole number of rulers can fit, we just don't count the last ruler because its whole length is not in there. So exactly when a new ruler can fit in, it jumps, okay? And we will see, by the way, eventually, that this is one disadvantage the ruler method has, and that the next method we're going to see doesn't have, which is why the other method is usually used in the real world. Alright, so now we'll try to also get the dimension of the Sierpinski triangle, okay? So here we use box counting, and box counting is simply the 2-dimensional analog of the ruler method, right? You make your unit squares smaller and smaller, and you count how many are inside the shape, okay? So we generate our Sierpinski triangle. And we actually, where is it? We save it as pixels with a very high resolution. This is a very convenient way of doing it, okay? And then, what we do, there it is. We just generate an array of all the pixels and say that this array is 1 if the pixel isn't white, which means it's part of the shape, right? And 0 otherwise. I'll just remind you of what the shape looks like. It looks like this, right? So wherever it isn't white, it's part of the shape. And then we split for some r, our r by r unit, right? We split the plane into r boxes, or rather boxes of size r, right? basically what we do is, if this is the Sierpinski triangle, we split the plane, okay? And the box length is R. And as R gets smaller and smaller, our resolution gets higher and higher, and we can count more precisely how the amount of boxes goes, right? So we just batch these in to R by R cubes, and then we just sum up, we count the amount of cubes, or boxes, sorry, that have any non-white pixels in them. And that counts us the amount of these boxes that have part of the shape in them. Okay, so these will be counted, but this pixel, for example, or this box, will not be counted because it doesn't have any part of the shape. Okay? And we run this and plot it for various R values, and we get this. And the dimension of the Sierpinski triangle turns out to be 1.56 or so. Okay? By the way, you can see here, even though I've plotted many less points in general, this method is much more stable, much less jumpy, and goes very tightly over the trend line, right? All right, and by the way, just for some intuition, you can see that the dimension of the Sierpinski triangle is higher than that of the Koch curve, right? The Koch curve had 1.25. This has about 1.56, sorry. About 1.56. What does this mean intuitively? If you look at this, the Koch curve, you can see that even though it's dense, it has a lot of gaps. It's pretty airy, right? But if you look at the Sierpinski triangle with a big, you can see that even though it has no area, as we've just shown, it's more solid. It's like it covers more of an area. It's closer to being an area than the Koch curve, right? And that's why its fractal dimension is higher, because it's closer to a plane than a line, right, than the Koch curve. All right. So now we ask an interesting question, which is, what is the coastline of Britain, right? If you remember our definition of a fractal from the beginning, it's a shape with arbitrarily fine detail, right? If you think of a coastline of a country, it has detail from the level of continents and the globe all the way down to individual grains of sand going up and down on the plane. And so you might guess that maybe coastlines of countries are also fractal shapes, okay? And that's what we're gonna test. So this is just a library that brings you geographical data of various countries, okay? So I get the country border. It just takes from the library. This is the highest resolution. And then I take whatever country I want. And I take the mainland, meaning the highest, the biggest landmass, right? Because we don't want all the tiny islands. That's not what we're testing, okay? So in this case, I take the United Kingdom, and I draw the border. It just draws the points, and I get its coastline. This is just its standard coastline. All right, maybe squished it. And now I'm gonna do the ruler method exactly as I've done for the Koch curve, right? I go over the points, and whenever I find an R distance, I count a ruler, and then I keep going again, okay? So this even uses exactly the same function, count rulers, and we go on R values for various R values, and we plot it, and we get this. And the dimension of the coastline of Britain is about 1.25, okay? So this is a 1.25 dimensional coastline. We can see that as we make our rulers smaller and smaller, the length of the coastline doesn't scale like a normal one-dimensional shape, right? It scales like a 1.25 dimensional shape. We can also do this for various other countries, like South Africa, Australia, and Norway, for which we do the exact same process, and we get, for South Africa, that it has a fractal dimension of about 1.05. And that makes sense, because even though it has some wiggles here, it's mostly flat and uninteresting, right? So it's much closer to a line than to a plane, the coastline itself, okay? Australia is a bit more interesting. It has a fractal dimension of about 1.1, right? And you can see that it's much more interesting and has much finer detail, right? And Norway, which is by far our most complex coastline, has a fractal dimension of about 1.34. Okay, so you can see that these parts really contribute to the fact that this is a very fractal shape and sort of covers a lot of the two-dimensional plane, right?
Why didn't you do it to Israel too?
Yeah, good point. Can we do Israel?
Can you do?
If they have it in the library.
They do, but they don't include the Yodav Shemot.
באמת?
So don't do it then. Oh my gosh.
All right.
No, but the coastline. But for the coastline, it doesn't matter.
Doesn't include.
No, but for the.
יהודה ושומרון זה לא על ה...
Oh, but it's not the coastline, it's the border. Rather.
It's the border.
Yeah, because coastline is a line, right? It's not a closed shape.
Okay.
אבל יהודה ושומרון זה לא בגבולות.
Can you do it anyway?
No, do it. Let's see, because it's. Let's see if they have. That takes some time. No way it takes the longest.
There it is. Whoa,
Why?
that sucks. All right. In a wow. No, never mind. All right, we can't do it for Israel.
Yeah. So.
Oh, my guess is perhaps Israel is too small, so for perhaps some ruler size it went out of bounds or something.
So I had two students do this a couple of years ago, and they didn't have the sophisticated library. They just took.
Books, yeah. You told us that they counted.
Yes, and so they had, but it was pretty easy for this. So they just took from Google Maps or something, and then did it the ruler method, and they got some fractal dimension of 1.01. Okay, so it's a line, but it's a little bit.
That makes
it
sense.
gets a little bit fractal because of Akko and Dreifach. So
Yeah, you can see here it's the most sort of complex part of the curve.
Yeah.
All right, so probably some ruler size it doesn't fit.
Then probably it would work for the box counting.
Yes, it probably would. I'll try it.
Yes.
All right, so if you remember from before, I said that the ruler method, as you can clearly see here, is not the most stable, okay? Not always does a whole number of rulers fit, and in general, it's just less accurate, okay? So here we show that the box counting method is more accurate, okay? So for the coastline of Britain, we do it with box counting. We just split the plane into boxes, and every box that has at least one point of the coastline inside of it, we count, okay? So we do that, and again, we just round all of the points to a grid and count the amount of grid squares that have any point inside, okay? So we can see box array at some point equals 1 if some aligned to grid point is on. Oh, I did this for Norway. Okay. So you can see this, okay? This is much more stable, especially as we get here. This is very numerically stable and very tightly goes around the trend line, okay? And it gives
up just to that we see the comparison from Norway. Yeah, you see
that this goes up and down, and even here it's not very stable. This is better. Okay? It brings a similar result of 1.34. Okay? And it clearly shows that the box counting method is much more stable and much more accurate. That's it.
Yeah, can you now instead of Norway?
Oh, Israel?
Yeah.
Alright.
Let's see, I mean the box counting should work. Wow.
It's less than
less than a line.
Because I'll explain why. Because when it gets to these values, the resolution of the actual measured geographical data is not good enough, and some boxes even here can't count any points, right? So maybe if I truncate the R values, then
No, but it's good. We want to be special, you know. We want
Yeah.
to be below
we're the
one.
only country that doesn't have a
We
1
want to be
keyboard.
below one.
Yeah, this is
No,
it's
that's good.
Okay.
All right.
מה שינית?
What?
What did
When
you
the
do?
boxes are too small, because the resolution of the data is not good enough, some boxes that look like they should count something don't have any points of the border in them, right?
But now we are similar to South Africa, and this sucks. Okay.
All right,
Good.
that's it.
Very nice. Any questions?
Very good.
Yeah. Nice.
Why didn't talk about non-mathematical fractals? I don't know what was the subject. Maybe it was only the
Much
method,
non-mathematical.
like trees or mountains, or just
No,
for the.
because
It's beautiful
He
to
didn't
see.
ask it.
No, I didn't
okay.
ask him. I asked him as an example of non-mathematical.
Yeah, we
just
asked
the
coastlines for that.
But
it's good idea.
I found in Wikipedia they have like a really beautiful picture of mountains. Like you put on a grid and it's like a fractal grid. I don't know.
Yes.
I'll show you
So
later.
maybe
Yeah, no, that's you can also do. You know, there are some people who do this in medicine. They take tumors and they calculate the fractal dimension of tumors. And it turns out that the higher the fractal dimension, the more dangerous the tumor is. You know, and,
Wow.
and the more difficult it is to operate.
Wow, because it's
We-
like more
Because it's more spread, you know,
Yeah,
it's less, if it's just a gush like this with clear boundaries, it's easy to take it out, but if it is, so you can,
So if it's not a perfect gush,
yeah,
spread out.
right.
So
And-
the fractal
and
dimension is
depending-
higher.
Yeah, so you can use fractal dimension, I mean, nobody has the patience to do this, you know, but somewhere there are some researchers who work on this, and I mean, you can do fractal dimension for everything. I told someone, I don't know, who asked me about fractal dimension in physics, how much it is used nowadays.
Yeah, Oz. Oz.
Yeah,
Oz,
right. And
when
I
we
told him
learned
that I had some students from Yossi Shurun. They studied the in superconductivity. You have sometimes this. You know, when the magnetic field is, entering the superconductor, how do you call this?
Inducing?
No, you have,
Yes, no.
there's a special term I forgot.
EMF. EMF.
No.
Yeah.
I forgot. Anyway, something
Not electric mechanic.
superconductivity. No, it's how, so they calculated how the external magnetic field entered into the superconductor, and this has special geometry, and you can calculate fractal dimension based on the strength of the external magnetic field, which is was interesting, but I don't know how practical.
But it's not a really big field in maths. Like I feel like it's not talked like people don't talk about fractals a lot. It's like
It's a little bit. There was a hype in the 2000s, and every generation has a hype, you know.
Yeah.
And 20 years ago it was fractals, or maybe 30 years ago it was fractals and calculation, and then it was networks, and nowadays everybody talks about AI and quantum computers. So, and in 20 years from now, this will be alte Geschichte, and there will be some new stuff, you know.
But it was a trend around the time chaos was studying physics, so it's not connected.
Yes, when you had all this chaos hype,
Yeah.
then you talk about fractals.
And everybody like research chaos.
Yeah, there were lots of papers, and this is basically when I started to learn, you know, and I stuck with it because I somehow like it. Good. I wanted to show you something very cute. Because this morning I was really amazed by this, so I wanted to share this. my former student, Asaf, here, he just there's some app on Google where you just upload your thesis, or you can upload whatever you want, and then it generates a podcast from your thesis.
Wow.
Check this out, it's amazing. I just give you 1 minute of. He just uploaded his thesis, you know, he finished his thesis 1 year ago.
And you can upload any article you want and you
can upload anything and they make you a podcast.
Can you show how it sounds, like if it's interesting or it's like
book? This is what I'm going to show you.
It's good for the seminar because we have seminar and then to listen to the article is better.
Yes, yes. But it's not really reading the article, it makes
make a story.
Yeah.
It's a story.
It's good.
Listen to this.
It's kind of mind-blowing when you think about it. Your body is this incredibly sophisticated network, almost like a biological internet.
Yeah,
wow.
There's constant chatter happening, signals constantly being exchanged between all sorts of different systems just to keep us functioning.
That's a great analogy, and that's really the essence of network physiology. Instead of looking at, say, heart in isolation.
So he wrote his thesis about network physiology applied to people who have sleep apnea. And they got it, I mean but the AI, this is...
We're just focusing on the brain.
Right.
It's about understanding how all these different parts of the body communicate and interact as a unified whole.
Okay, let's unpack this.
That's crazy.
For this
He
deep
did
dive,
it,
we're going to look
or
at
he found it.
really fat.
It's called Notebook LM.
But he found it like
some
no.
friend called him and then he uploaded and he sent me this morning and I was shocked, you know. I almost
It's mind blowing.
I almost choked on my coffee. I mean, how can they this better explain than I could ever do? So yeah, it was.
They sound like real. They sound like the, you know, like 2 months ago when you heard AI, it was like some programmed voice. You can hear it's AI.
Yeah.
They sound like real people.
Like real people talking, and they are not. I heard it's 15 minutes, now 18 minutes, and there's no stuyot. It's exactly on the point and explained very well. Don't know what I'm doing here anymore. It's just I upload my lectures to this, make a podcast, and go home. Yeah, good. So that's about this. We last time we talked about networks, or a couple of weeks ago, and we discussed several. What are the 2 main types of networks that we discussed? You remember?
The rich get richer one. I don't remember.
Yes, you had the rich gets richer. That was power law, right?
Power
and you had the exponential. The rich gets richer. Power law network was related to airline networks, right?
Yeah.
And the exponential random network, so to say, was related more like to roads, right? How streets or roads go out from a town. And then we had here a model. You remember this model that could simulate such behavior, this power law. And how did they do it? They constructed a Erdős-Rényi random network, and then they added links. This is a new node, and you add links to the most popular, or preferably to the most popular links. This is the rich gets richer phenomenon. And now I want to continue a little bit along these lines, because if you remember, this k to the power minus 3 is not what they found empirically, right? Empirically, when you look at the World Wide Web, for example, you get a different power. You see this? 2.45 and 2.1. And then people started to do research in order to reproduce these results. How can I get something below 3? Okay, between 2 and 3. And so what would you say? I mean, when you look at the World Wide Web and you get there an exponent that is below 3, between 2 and 3, what would you add to your network model in order to reproduce these results? I mean, how can you make your model more realistic, so to say? What do you have in the real World Wide Web? Any ideas? You don't just add nodes. I mean, this algorithm just added nodes according to the rich gets richer, but you have also other phenomena in the real world, right? So what would be your approach if you were to do some research on making this model more realistic? Any ideas? I mean, what does this model not take into account? Let's say Lehman Brothers. Do you remember Lehman Brothers? No. Yahoo. Remember Yahoo? Awesome. You have also companies dying, you know, and then they disappear from the
like
web.
the rabbits.
So,
They're like the rabbits.
No. No, but you have nodes. I mean, you also have nodes that are aging, or sometimes they get less popular. You know, now a couple of years ago, something I don't know. What is a good example? What was popular? Nokia. Okay, in the 2000s. Everybody remembers Nokia?
Yeah.
So they were a big hub in cell phones, in mobile phones, and Samsung was a good skiller. I remember I got Samsung, all my friends said Nokia. Oh yeah, Samsung. Nowadays, you know, Nokia, who gives, nobody looks at it. So you have aging inside, right? And so you can now start to look at these models and see, so this is the original model, gamma is equal to 3, and now you can say, okay, sometimes only in the beginning something is attractive and it disappears, the attractiveness over time. So this is one kind of research they did. You have here the deletion of node, right? When some company goes bankrupt or whatever, you have accelerated growth, something is not just linearly attracting new nodes, but exponentially. For example, you have the aging that we just talked about, and then you have these internal links. So all kinds of different models or modifications of this Barabashi-Albert model appeared that tried to modify this power law. And here, just to round this up, the original Barabashi-Albert model had a preferential attachment that was k to the power 1, right? K to the power 1 that we just saw. And now if you generalize this and you say, okay, we make it k to the power alpha, and now we look at alpha below 1, for example 1/2, what's happening, and what's happening when alpha is above 1. And what you see here is a fundamental change in the network topology. This is the original with the power law, and you have a few big hubs, right? We talked about this last time. So what happens when you do alpha smaller than 1, if you put 1/2? Then you have you get this kind of behavior, and this looks like more like the random network, right? The Erdős-Rényi network. You don't have hubs anymore so much inside, so this is more, you can say, so no preferential attachment, exponential. This looks more like a communistic network, right? So to say, everybody is more or less equal, okay? Yeah. Equally poor and miserable. And then you go to the case where you are above 1, so this is 1/2, and what happens then? You get 1 or 2 hubs that dominate the whole network. this is a very capitalistic model, where also everybody is miserable except these two guys who are the big ones, okay? So we are living here and we're also miserable, but we would be worse off here or here, right? So just to show you how you can change this parameter here of the preferential attachment, and you change this power law into an exponential or into something that is even more, has even a fatter tail than the power law here that we achieved. Okay, and now we want to talk about what happens when you delete nodes. Okay, about the robustness of the network. So you can say that if you have this as a network and you start to delete links, nodes in this case. You can also delete links, but let's stick to the nodes. So if you would take out this node, okay, so in B this node is taken out, the network still functions, right? I mean, maybe these nodes here that are connected to the one that I took out, they are a little bit less well working, so to say, in transmitting signals, or it has a longer transmission time, but the network is more or less still functional. So then I say randomly I delete another node, okay? So this one, no, wait, this one I delete, and then I end up with this network. And then you see already that we have disintegrated the network, right? So these two guys and these two guys, they are disconnected from the main network, so to say. And then you take out this one, and when you do this, you completely disintegrate the network. So this looks very much similar to a problem that we discussed earlier in the course, and this was related to calculation, right? We said the opposite. We added nodes, or in this case we added bonds or sites, and we built an infinite cluster, right? So in this case there would be no infinite cluster, and then you would add a node here, which is this one, for example, and then you build an infinite cluster. Okay, so when we study, or when people study the robustness of networks, they basically study a calculation problem. Okay, you say, good, I have here a fully connected network, close to fully connected network, and then I randomly destroy nodes, so to say. And I, of course, my P infinite is decreasing until I get to a critical point where I lose to have an infinite cluster, or in our world now a network that is working. And so this way you study the robustness of networks. And next week we have someone talking about this on a real world example on the airline network. Right.
It's very similar to critical temperature. It's something that is similar
to temperature.
Yes. For example, the magnetism of paramagnetism of
This is percolation. We made this comparison of percolation and magnetism. I mean, the phase transition between ferromagnetism and paramagnetism is like percolation and non-percolation. Infinite cluster, no infinite cluster. Yes, and you find also the same power laws, however with different exponents. But it's this is the physics relation to it. You're right. So next week, B'ezrat Hashem, we have somebody who is showing us something about the robustness of the airline network. And the question that I posted, I don't know, I have to see if it's true, is you want to go for vacation from Tel Aviv to Honolulu, okay? There's no direct flight from Tel Aviv to Honolulu. You have to go, you have to fly to different airports. And what happens now when the airline network is disturbed by whatever? There was 10 years ago a volcano in Iceland was erupting, and this disturbed all the flights that went to London, I think. London to the US. It was 15 years, I don't remember. So then you had to go to Honolulu. You had to go maybe not to, I mean, usually do you go to the west or do you go to the east to Honolulu? I don't know.
Where is Honolulu?
Hawaii. I don't know. So you can go to the east or to the west, and when you cannot go to the US, then you have to go over Japan, right? So, but it will take you much longer. And then you can also take out some airports in Asia, and then it will make it even more difficult to reach Honolulu up to a certain level that you cannot reach Honolulu at all. Okay, so this would be your, spoken in our terms, that the infinite cluster is completely disassembled. Okay, you don't have a functional network anymore. And hopefully next week we hear about this. Okay, good. So that's about the robustness of networks, and now I want to talk about a field of research that was actually, don't want to say invented in Bar-Ilan, but Bar-Ilan was a pioneer in describing such kind of networks. And what triggered this research was done by Shlomo Havlin when I was a PhD student, and what triggered this research was that he was fascinated by the interconnectedness of different networks in society, right? So you have infrastructures that are very dependent on each other. So you have the electric power grid, which is a network of itself, depends on the natural gas, right? On the transportation network, on telecommunication network, right? That synchronizes different power plants, on the water network, oil, and whatever. And it's very complicated, very complex, so to say. And he tried to model such interdependent structures. And push to his research was something that happened in 2011 in Japan. I don't know if you remember, there was a big tsunami, right? So this big tsunami actually caused exactly what you could predict from such interdependency. It showed a cascading disaster. So first, the tsunami, the waves hit a big power plant, right? I mean, they hit many things, but they also hit this big power plant in Fukushima that was providing a lot of electricity to a big area. That was the only provider of electricity in a certain area. When this collapsed, everything else collapsed. You know, there was no communication network and so on. And really, the paper that they started to describe this phenomenon was motivated by the electrical blackout in Italy in September 2003. We had recently a big blackout in Spain and Portugal, right? But they haven't finished yet the analysis, but I assume it was some similar mechanism. And what happened here in Italy was that you had so on the Italian map here, you have all the power plants plotted, right? And here in the air, you have the communication networks. plotted. So communication networks are just above. And what you see here is that you have a link. You have links between the power plants and the communication networks because they need to communicate with other power plants in order to synchronize their activity, right? So in this case, a power plant in the center of Italy stopped working, it was malfunctioning, and this caused several communication networks to lose electricity, and they stopped working also. And when they stopped working, all the power plants that were dependent on this communication networks, they also stopped working. So you had, in this case it was only one, but this network, this electricity, this power plant was again connected to these two power plants. They were connected to other communication networks, and this way very quickly you see that you disintegrate half of Italy from the power grid, so to say. And what's also important to mention is that we have here two kinds of links. Okay, this is very important to understand. There is links between the power plants that are the regular links that we discussed so far when we talk about networks. But then you have these interdependency links that are connecting two different kinds of nodes. Okay, so the interdependency links, they connect here the power plants to the communication network. Okay, and when they fail, they cause this cascading failure. Yeah, and nowadays there is the last 10 years, 10-15 years, there is research on these kind of interdependent networks everywhere in science, because it appears to be these interdependent networks you have in the life science, you have in technology, you have everywhere in nature. When you look at physiology, what I just, this podcast that I played you, this was work in network physiology, where we study how different organ systems communicate with each other. And this is important, for example, when you go to the intensive care unit and you have there some phenomenon that's called multiple organ failure, that when you have, typically it starts with the liver or the kidney, and this triggers the collapse of the whole body, right? And because everything is connected with everything in the body, and but it is important for physicians to understand where to help first, right? I mean, which link is the most important, so to say. And so this is one example of an interdependent network in physiology. You have also in biology, you have transportation, railway networks are connected with airline networks and so on. And then you have this critical breakdown, or the breakdown threshold for these interdependent networks that are important to understand. And here is a summary of the work that the Purp did on these networks and networks. So they basically started to just connect 5 similar networks, right? Okay, so here you can connect them in a line shape in this kind of star shape or this F shape, and then you can study what happens when so here I have an example of 4 networks connected. Red are the interdependency links, and then you can perform this kind of calculation analysis that we just discussed above, and see when the network breaks down. Okay, when this whole this network of networks breaks down. And what you see here, again you have P infinite over P, and now you remove randomly these interdependency links, and what you see here, that when you have a network of networks that has 5 networks contained into it, you get a much earlier this breakdown, okay, than when you have only 2 coupled networks, okay, and this is the case when you have the network. I mean, the normal percolation transition is this case. So you have basically a switch also from a first order phase transition to a second order phase transition. And yeah, you can even show this analytically, that so P infinite is equal to P1 minus e to the power minus k P infinite. This is for regular Erdős-Rényi network. And now when you couple 5 different Erdős-Rényi networks, in this case, or in this case it doesn't matter, you just obtain here an exponent n, and this yields this behavior that you have a breakdown much earlier, and you have a first order phase transition versus a second order phase transition for Erdős-Rényi. And only recently, in the last 2 years, so this is all theoretical work. I mean, nowhere in nature you have 5 Erdős-Rényi networks coupled in this case, right? And Shlomo worked together with Aviad Friedman to realize such a system of interdependent networks. So what they did is they used 2 semiconductor networks. Okay, you see here semiconductor network, here semiconductor network, and they have their electrical links, so to say. And now you put them close to each other. Okay, that the links that you have between these 2 semiconductor networks are thermal links, okay? Different kind of links, thermal links between the 2 layers, and then you study what happens when you increase the temperature, right? Or decrease the temperature, whatever. So you start, let's say you have a separate top and separate bottom, and now you increase the temperature, and you lose your superconductivity by around 2.5 Kelvin in this case, and 2 Kelvin in this case. And this is also something that the theory would predict. But then you go to the coupling. Okay, now you couple them. So then you see in this case, these are the 2 the squares here. I don't know if you can distinguish this. So here you have again the separate bottom and separate top, and now you couple them, right? And you see that you have the critical temperature is shifted to lower temperatures because they are now coupled. And this is exactly what you would predict by this theory that I showed you before. Okay, with the P infinite and that you have here a power of 2 in this case, right? Because we have only 2 layers, and you reproduce very nicely the theory. So the theory is this, and this is the experiment, and it went into Nature Physics because of this. But this is the first realization of an interdependent network in the lab in physics. Good. Any questions for this?
What's the red in the picture?
This one?
Yeah, the red.
So this one are the links. The dependency links here is basically heat columns, so to say. Okay. And when they are too when this coupling is too strong, both of the layers will lose their superconductivity. Okay. So if you so in this case you make them stronger, and you kill the superconductivity. It's a little bit the opposite of before we saw the links getting weaker, and that's why the networks disintegrate. Here, this happens when the links get stronger. Okay, but still, it's the same physics, so to say. Good. Okay. Then, thank you. And we'll see each other next week. There's nothing next week, right? No. Shavuot is finished then, and no more vacation until the end of the semester. Good. Okay. So Chag Sameach, and see you next week.